Hello everyone, welcome to ExamRat. My name is Shatabdi, I'm a second year medical student. So today we're going to be talking about refraction. We had already done a class on reflection. We talked about refraction in our own human eyes. We talked about defects of vision, where we talked about myopia, hypermetropia, and presbyopia. Myopia standard for nearsightedness, and where the person could not see distant objects. So its corrective lens was concave lenses. Why? Because it was a diverging lens. Similarly, hypermetropia we talked about, where it was the opposite. It was farsightedness. The person had problem in seeing near objects. In that case, the corrective lens was convex lens. So we talked about how refraction happened in human eyes. So today we are also going to talk about reflection through particles in the atmosphere. But before that, what we have to understand is that reflection of light through a prism. Okay. So what is a prism exactly? It is basically a triangular. It's basically a triangular structure which actually has 6 sides, but here we can just see 3 because it's a 2D board. So basically what happens is, I told you when we talked about reflection through a glass slab, that reflection was happening twice, right? First on the first slab, then it was entering, and then again it was moving away from the normal, and we had talked about how lateral displacement was happening. So in the same way, prism is also similar to a rectangular slab, just that its shape is different. Here also reflection will be taking place twice, and as you can see in this picture, it is happening twice, once here and once here. Okay, so again we will talk about the incident angles, we will talk about the refractive angles. So again, when you are drawing a normal in a slanting surface, the logic is simple. You always have to make a 90-degree with the surface. So in this case, it is coming like this. Similarly, this is a normal and this is also a normal. So this is I1. Okay, so the ray gets refracted, and this is R1, this is R2, and finally this is I2. You can also call this as the emergent ray. Okay, where is it? It is at the point of refraction, which is the second refraction that is happening when the ray goes out of the prism. So here twice refraction is occurring. Okay, when we talked about refraction through a glass slab, we talked about the fact that this distance, the distance between the incident ray extended and the emergent ray, is called the lateral displacement, right? Here we are going to talk about something else, that is d or delta or angle of deviation. So what is it exactly? It is, again, if you extend the emergent ray backwards and you extend the incident ray forward, then you will get an angle. This angle will tell you the angle of deviation. So what is deviation? Deviation means anything that happens that deviates from its actual path, right? Like that sets away from its actual path. So this is the angle of deviation. Okay. So all you have to know here is you have to name the angles properly. You have to talk about the angle of deviation. And this angle, angle A, this is known as the angle of prism. Okay. So one interesting fact about angle of deviation is that when you see, this is the angle of incidence. Okay. And this is angle of deviation. So when we draw a graph, as and when we are increasing the angle of angle of incidence one by one, we see that the angle of deviation keeps decreasing, right? But this happens till a point. After the angle of minimum deviation, which we call it, that is the capital D, this is your angle of minimum deviation. So once this point is reached, after that, if you keep increasing the incident angle, then the angle of deviation will again increase. So what I mean by this is that if this is a prism, okay, so here let the angle be about 50 degree. Okay, so this is the incident ray extended, this is the angle of, roughly the angle of deviation. Okay, next time when you are again drawing an angle, this time when it is 60, like when you increase it, and let's let the angle be now 60 degree. What will happen is that the angle of deviation will decrease. So as and when you are increasing the angle of incidence, your angle of deviation keeps decreasing, but this will happen till a point till minimum angle of deviation is reached. After that, if you again increase the angle of incidence, so after del min is reached, then if you keep increasing the angle of incidence, your angle of deviation will also increase. So that is what this graph depicts. Okay. Next we come to another interesting concept, that is refraction of white light through a prism. So white light is a monochromatic light, right? But the light that comes through, that we see, even though it is white light, but it contains all these 7 colors, right? Since refraction happens very less when there is a clear sky, or when there are almost very less water particles, there's very less scope of white light to get refracted. So what happens is that the light that directly comes from the sun, we see it just as it is, which is white. But if you have observed that sometimes when we see rainbows, or rainbows is also a very rare concept, just the very basic thing of when we see the sky as blue, okay, and during noon how we see the sky is completely white, and then as and when evening occurs, we suddenly see the color of the sky changing. Now why is it happening? If only white light has come to us from earth, then at all times we are supposed to see white light only, right? But we don't. That is because light light that comes from the sun, it contains all the colors, it contains the whole picture within it. But since all of them have different wavelengths, and you know that different wavelength means different speed, right? So more the wavelength, more will be the speed. Okay, so since they have different wavelengths, so they get scattered differently, and we see different colors at different times of the day, and if they do not get refracted at all, we see the whole light, which is the white one. Okay, so refraction of white light through prism, what happens is, like I told you, that as soon as it gets refracted, since all the colors of the picture have different wavelengths, they get scattered, like individually they get refracted the second time. So this was the first refraction, and this was the second refraction. So by the time the second refraction happens and it comes out of the prism, it has dispersed into its individual colors. So how exactly does the wavelength differ? So remember, like I told you, that the wavelength is dependent, like this wavelength and frequency both are dependent on the speed of the light depends on both of them. So in this case, if I talk about the wavelength only, more the wavelength, less will be its deviation. So what I mean to say is that more its wavelength, the less it is likely to deviate from its original path. So like you can see here, if I had extended the incident ray, it is almost parallel to the red, right? So in this case, the angle of deviation, you can very well understand how small it is. So that means since red has the greatest wavelength, or it has the greatest speed, so it will it will deviate the least. Okay. Next comes orange. Orange's wavelength is second highest, so it will deviate the second highest. So like this, what happens is that by the time you come to violet, so you understand that violet gets deviated the most because its wavelength is the lowest, so its speed is the lowest. Its deviation as a result of it is the highest. It gets deviated the most. Okay. So this is the whole concept of Vibgyor, how refraction through a prism basically disperses all the white light into its individual colors. So the band of the colored components of the light beam is called spectrum. So this whole band is known as spectrum. Okay. You might not be able to see all the colors separately, but you can understand that they are distinct from each other. This splitting of light into component color is known as dispersion. So this whole process that is happening is called dispersion. Now, different colors of light bend through different angles with respect to the incident ray as they pass through the prism. The red light bends the least while the violet bends the most, and you know that because more the wavelength, more the velocity or speed of light, and less is the angle of deviation. Thus, the rays of each color emerge around different paths and thus become distinct. Okay. This is a very interesting picture where you can see how the light has divided into its components, and again, if you put a prism, but if you invert it, then again it will emerge out from the second prism as white light. So that is another interesting aspect of prisms. Isaac Newton was the first to use a glass prism to obtain the spectrum of sunlight. So he used this on sunlight and he saw how sunlight got dispersed into its different colors, into its polychromatic colors. Thereafter, people started understanding the concept of rainbow, that what exactly happens in it, that it is the same thing, that how light rays get refracted first. And what happens here, if you are noticing that if here it's refraction, then here it is reflection, right? And finally, the violet and the red, they disperse out. So, how is reflection occurring inside a solid? To understand that, we have to first understand the concept of critical angle. So critical angle is nothing. It is basically, let's say this is a rarer area. So critical angle is the angle formed by an incident ray in such a way so that its refracted ray is normal to the or parallel to the surface. So for a ray to have for an incident ray to have its refracted ray exactly parallel to the surface, what this angle is going to be, this angle is known as the critical angle of this medium. So the incident or the angle of incidence for which the angle of refraction is exactly 90 degree is known as your critical angle. Okay, or we denote it by C. Why are we talking about this critical angle is because if you can understand something is that first when I started giving rays less than the critical angle, like a ray went like this, so this angle is lesser, then this one, it is again lesser, then slowly it went up to this ray, like we used this angle for which we saw that the refracted angle is 90. So what is the next step going to be? If I increase the angle of incidence more than the critical angle, then what is going to happen next? I1, for example. What will happen is that now every ray will get reflected, because now it will, like for the first and the second ray, what was happening, that it was going and then it was again going in the rarer medium, but it was more away from the normal, and ऐसा करते करते finally it reached a point where it was exactly parallel to the surface. So now if we then again increase the angle of incidence, and now it has no way to go up, right? It has no way to go into the rarer substance. So what will it do? It will bend into the denser medium itself. So now then it will come here, as a result of which we get a total internal reflection. This phenomenon is known as total internal reflection. So why are we calling it as total internal reflection? Because it is happening in the denser medium only, where the denser and the rarer medium, where the incident ray and the refracted ray both are on the inside the same medium. So what are the criteria for a total internal reflection? That the ray has to travel, for total internal reflection, ray travels from denser medium to rarer medium, right? Okay. Also, angle of incidence is greater than angle of or critical angle. In both these two cases, critical total internal reflection will happen. So if you notice that in the rainbow, what is happening is that first it is going, it is getting reflected, and then here what is happening is that total internal reflection is happening. So for some reason, basically this angle of incidence, you can say, has crossed the critical angle. Okay. So also what you can understand here is that we can calculate the refractive index also of this substance. So what we say is that refractive index of the second medium with respect, in this case we can do as refractive medium of the first medium with respect to the second, like if we have to calculate the refractive index of this denser medium. So in that case it will be speed of light, let us call it v, by speed of the light in the rarer medium, right? So let it be v1. And you know the other formula, which is sin I by sin r. So mu 2 1 would have been sin I by sin r, right? Or in this case, sin r is 90 degree and sin I is your critical angle, right? Sin C. Since I've reversed the whole thing here, so here it will be sin 90 will be in the numerator, and sin C, you know, sin 90 is 1. So refractive index of the denser medium will be 1 by sign of critical angle. Okay, so this is another way of finding out the factor by which the ray has bended, by finding out the refractive index. So here refraction occurs, then total internal reflection occurs, and finally, since the refraction had led to the dispersion of the individual lights, so now reflection also will happen of the individual lights, and we get to see the individual lights emerging out of the raindrop here. So why does the rainbow always occur after raining? Because the water droplets present in air after the rain, they will disperse all the lights. Okay, as a result of which we see the rainbow. So now here refraction is happening once. So now when this ray again, so for example, refraction is happening, and then again here also, so there's like, it happens like a chain, and so we see a huge rainbow over a large surface because it happens one by one. Okay, so now we talk about atmospheric refraction. Its basic example is that twinkling of stars. So what is exactly being said here is that the starlight on entering the Earth's atmosphere undergoes refraction continuously before it reaches the Earth. What is the difference between space and atmosphere? Space is vacuum, right? It has no air particles. Where atmosphere has lots of air particles, gases, this and that. So obviously there are lots of particles here. So when there are particles, there will be refraction. So the starlight on entering the Earth's atmosphere undergoes refraction continuously before it reaches the Earth, right? The atmospheric refraction occurs in a medium of gradually changing refractive index, yes. Since the atmosphere bends starlight towards the normal, the apparent position of the star is slightly different from its actual position. Okay. The star appears slightly higher than its actual position when viewed near the horizon. Okay. Further, this apparent position of the star is not stationary but keeps on changing slightly since the physical conditions of the Earth's atmosphere are not stationary. Since the stars are very distant, they approximate point-sized sources of light, and as the path rays of the light coming from the stars goes on varying slightly, there is an apparent position. The apparent position of the star fluctuates. No need of this line. So you just have to remember this. So what is basically being said here? It's that when the light is coming from the star, it is getting refracted, and then again refracted, and then again refracted, and then again refracted, right? So here let there be like lots of particles for which the refraction has taken place. So finally, when it is, and always remember that it is bending towards the normal, right? Because why? Because space compared to atmosphere is rarer, denser. Then as and when you move to the farther layers of the atmosphere, you're moving towards the core of the Earth. Obviously, the number of gas molecules, water vapor, all are increasing. So then this becomes rarer compared to this. So always the bending is happening towards the normal, right? So when we are seeing it finally through our eyes, where are we seeing it? We are seeing it somewhere here, right? So the apparent position of the star has changed. Now what happens is that since the distance, since the starlight is traveling light years distance to meet our eyes, so in between lots of things can happen, like raining, and then the earth constantly revoluting, rotating. So due to all these reasons, the light always does not come to us constantly. It sometimes bends and comes to us in a different way, or it comes to us late. So during these times, basically the twinkling happens. Like we can once it reaches our eyes directly, then it reaches a little later, then it again reaches constantly. So this whole fluctuation that is happening, that is because of the particles present, the conditions that is happening, like whether it is raining, breezing, uh, humid, whatever, the fact that all the particles are constantly moving around the sun in an orbit, all these conditions taken together lead to the refraction of light in such a way so that the starlight coming to us, to our eyes, is not constant. It will keep fluctuating. So if you draw a graph, it will be like this. So this leads to basically the twinkling happening due to recurrent refractions and apparent change. Just give a star mark here. Apparent change in position of frames of references. What are frames of references? We had studied about it when we talked about motion. So if we are the frame of reference, and according to us, the light is coming from the stars, and when the stars are moving around the sun, then the sun is the frame of reference. So constantly the frame of references are changing, constantly the position of everything in the universe is changing, as a result of which the light is fluctuating, when it seems that it's fluctuating when it reaches our eyes. Okay. Next is scattering of light. Scattering of light is also something similar to what we had discussed in our first slide about dispersion. So it's one of the most important phenomena in our daily lives. It's seen by everyone from their childhood, where there's the blue color of the sky and the color of rainbow. Scattering is completely different from reflection or refraction. In reflection, the light goes in a straight line, we know. And in scattering, the light gets scattered in different directions by a medium through which it passes. So in reflection, there was only one way that the light would have moved, but what they are saying is that in scattering, the light will get hit once in the surface and then scatter to all different directions. That is the meaning of scattering. When a light ray passes through a medium, it strikes the particles present in the medium. That is, due to this, some of the rays get absorbed while some get scattered in all directions. Okay, what is the example now? When light strikes the particles in air, the particles absorb some light and radiate the rest in all directions except the incident direction. This is called scattering of light. The wavelength of the light and the size of the particle which scattered the light assists in determining the strength of the scattering. So basically this point is very important for scattering to take place. This basically tells us that when light rays are coming from the sun, okay, and there are very, very small particles present in the atmosphere, like extremely small, like refraction or reflection cannot possibly happen. So what happens in those cases is that, provided that the wavelength of the light rays is very, 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 very big than the size of the particles, what happens is that in this condition, this light ray, when it reaches when it strikes the particle, it gets scattered in all directions. So this is what is happening. So some of it gets absorbed, like say 10% of the light gets absorbed and the 90% of it is scattered. So now so many particles, millions and billions of particles, so many light rays coming every second, every millisecond. So obviously the scattering takes place via a huge area, right? So much so that the whole sky appears blue. Now why is it particularly appearing blue when Vibgyor has all the 7 colors, right? So basically what it is said is that blue, since it has less wavelength compared to red, like wavelength decreases from right to left, right? So wavelength keeps decreasing along this way. So since blue has a very less wavelength, so lesser the wavelength, more is the extent of scattering. Okay, provided that the wavelength will always be greater than the size particle. This is criteria 1, but the criteria 2 is that the wavelength in itself has to be less in magnitude, not less than the size of the particles, but less in magnitude. This will lead to its scattering more and more. Okay, so as a result of this, there is huge amount of scattering which makes the sky blue. So in the morning, if you see, up until the noon, we see that the whole sky is moderately blue. Now during the noon, like around 12 to 1, you will see that the sky is absolutely white. Now why is that? That is because initially the distance between the sun and the earth had been more. That is why it was basically, there was a huge distance, so the light got scattered by huge amount. But as and when the sun, the earth is also rotating and revolving around the sun as well. So as and when the earth is rotating and the sun is and it is revolving around the sun as well. So what is happening is that there comes a point when the sun is exactly perpendicular to the earth, or perpendicular to that portion that at where we are, for example. So in the morning, if we have seen the sky as blue, as and when the sun is getting closer, like the angle between the sun and the earth is getting lesser, the amount of scattering will lessen, because now the amount of particles between the sun and the earth is decreasing. As a result of which, when the sun is directly on top of the earth, like it can't be always accurate, but approximately when it is directly upon the earth, then there is no scope of scattering, then direct white light is coming. Now, so at around noon we see white light. Then we know that sunset is going to happen and the earth is rotating at that point. So at around 5 or 6, what is happening? We are seeing ekdam orange or red sky. Why is that? Because now the sun is moving very much away from the earth, right? Like very much away from that part of the earth which we are considering at this point. So if this was here and this was this portion of the earth that we had taken as the frame of reference, so this one, and now it is gone very far away. So if this is the sun and this is the portion of the earth we are taking in consideration, then it has moved very far away. So distance has increased a lot. Now you know that the rays of more wavelength will always travel farther distance than the rays of shorter wavelength, right? Like that is the whole advantage of having a longer wavelength, because it goes long distances. Okay, so here basically what will happen is that the red light or the orange light will travel the farthest. They will travel the farthest to reach that point of the earth. Blue light will get dispersed and scattered much before it reaches the core layers of the atmosphere, like the later layers of the atmosphere. So by the time we get to see the light rays coming from the sun, all the smaller wavelength light has already scattered, dispersed in their own way. What remains is the red or the orange wavelength lights. So that is why during sunset we see orange or red colored sky. So this is the whole cycle that happens in the 24 hours every day. The phenomenon of scattering of light by the colloidal particles gives rise to Tingle Effect. So what we just talked about, that is known as the Tingle Effect. It is seen where a fine beam of sunlight enters a smoke-filled room through a small hole. Thus, scattering of light makes the particles visible. Tingle effect can also be observed when light passes through a canopy of dense forest. Here the tiny water droplets in the mist scatter the light. Basically the thing is that it has to be tiny. The color of the scattered light depends on the size of the scattering particles, as I told you. Very fine particles scatter mainly blue light, while particles of larger size scatter longer wavelengths, obviously. If the size of the scattering particle is large enough, then the scattered light may even appear white. So, after a point, the dispersion won't happen anymore, like the dispersion of light into its 7 colors. So, as and when you keep increasing the size of the particles, you will find that the light of the more wavelengths are being seen, and after this, you know what will happen after the red light is being shown. Then you will just get to see the white light because no dispersion is happening, because you've increased the size of the particles by a very large amount. Okay, so to conclude our class now, I think you'll be able to answer why is the color of the clear sky blue. It is because in the clear sky, there is no water particles, which are large particles. We have very fine particles, and you know, the finer the particles, the less the size of the particles, the lesser wavelength lights will be dispersed by it, or scattered by it, sorry. So then we will see the blue light, right? And towards the sunset, what I told you, at the sunrise or at the sunset, the larger wavelength lights will be appearing, because the smaller wavelength has already scattered and they've already dispersed. So now what comes to our eyes directly are the longer wavelength lights, which are the red and the orange lights, because their wavelength is very high. Okay, so that will be all for the light chapter. Next, in our next lesson, we'll start with current. So thank you for watching.